Hi, my name is Mary Grace Carr, and this is my Lab 3, Magnetic Field of a Bar Magnet. Before getting into the presentation today, we'll first do a quick overview. So first we'll have an introduction to the lab, and then we'll go over the fundamental physics principles and ideas used in this lab, and then we'll go through the observations and procedures done to conduct this lab, and then we'll get into all the experimental data gathered and calculated, and then we'll go into the computational model that we created for this experiment, and then finally we'll end with a conclusion where we'll compare the results in a discussion. So first, the introduction to this lab. So the purpose of our lab is to measure the distance dependence of the magnetic field of a small bar magnet. We'll first measure our magnetic field of a bar magnet using a magnometer on a cell phone, and we'll examine how it changes with distance, recording these measurements. We'll then compare our results to the distance dependence for both the equations for on-axis and off-axis of magnetic fields derived from the Biot-Savart law, and then we will model this with GlowScript and compare. For the purpose of this experiment, our system will be the bar magnet and our surroundings will be everything else. As a preview of the main result, the distance calculated by hand and by GlowScript are nearly the same, but the magnetic field from both differ. So to talk about our fundamental principles and ideas used in this experiment, first we need to make sure that we have an understanding of bar magnets and how they work, such as the direction that their magnetic dipole points, as this is fundamental to our experiment as it forms the basis for investigating their magnetic fields. For magnetic field superposition, we need this because it allows us to consider the influence of all magnetic moments within the magnet, which is crucial for understanding the total magnetic field produced by the bar magnet. We also need to understand the magnetic field of a dipole, as this is essential as it characterizes the behavior of the bar magnet, which can be thought of as a magnetic dipole. The Biot-Savart law, we can calculate the magnetic field at different points around the magnet. It's applicable because it provides a theoretical framework for predicting magnetic field variations with distance. Lastly, for distance dependence, we need to investigate how the magnetic field strength changes with distance is the core of this experiment, and this allows us to explore and quantify the relationship between distance and the magnetics field. And you can see the two formulas for Biot-Savart law and distance dependence here. Moving into our initial observations, so we can see that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. However, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. This is not true. And then also what's not true is the position of the magnetometer has no effect on the measured x component of the magnetic field. But the last thing that is true, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. We need these initial calibrations to help us know how to work our magnetometer. So this is just a quick outline of the procedure for locating the magnetometer. I have some pictures taken here from the experimental guideline and my rules right here. And here is the next part of it. This is to measure the magnetic field and how that procedure was done. So what we're looking at here is the experimental data gathered after doing all of those steps just shown in the previous slide. I want to point out here that the distance is 0.2569, and this is our graph with this equation here. So next we had to perform some calculations in order to fit our formulas. So right here I show how we're calculating N and K, and this is taken from the graph from the previous slide. We're basically equating this formula here to y equals mx plus b, and you can see what our values are here. And then we're now setting these two equations for distance dependence and then the Biot-Savart law equal to each other, and that helps us to find our magnetic dipole moment, which we got to be 1.92. I'll now show our GlowScript code. So these are showing our initial conditions right here, and we can see that the dipole moment of the magnet, I put it here as 1.92, and these are some of our other initial conditions, and then this is the function to calculate the magnetic field. This is some more of the code just to create those arrows and to show the magnetic field, and this is the output of our results. You can see here this is illustrating the way that the arrows are pointing for the magnetic dipole moment and the field of the magnet. And then we can see that the D here is 0.259, as well as some other calculations here. So, results comparison. Our distance and our calculations in GlowScript probe were nearly the same, as you can see right here, but the magnetic field from our calculations is different than the calculations for the computational model in GlowScript. So some sources of potential error are other devices nearby that emit a magnetic field, such as steel, iron, or other electronic devices, or we didn't correctly align the phone to true north before beginning. So to answer these questions, For the first question, the results would vary by the x component, as the measured x components of the magnetic fields of the bar magnet would vary by the same amounts, as they no longer account for the Earth's magnetic field. By orienting at magnetic north, this canceled out the x component, which was equal to 0 for the problem. For the second questions, our results again would vary by the x component, as the new measurements would be multiplied by a scalar value, yielding the same results, but with a different higher magnitude, aka the magnetic field would increase. By sticking these two magnets together, we are essentially creating one stronger magnet. That is the end of this presentation. Thank you.